Chapter 6, Forces and Motion 2, free response question. So these are conceptual questions, and it's pretty important, I think. Okay. So can the coefficient of static friction have a value greater than 1? What about the coefficient of kinetic friction? Can that have value greater than 1? Answer to that is simply yes, right? Okay. When frictional force is bigger than the normal force, that can happen, okay? Since frictional force is equal to mu times the F normal, right? And because of that, mu is equal to F friction over F normal. So if F friction is bigger than F normal, that can happen, okay? So for mu of rubber, right? Right? Natural rubber is very, I guess, sticky, I guess is the word, right? And it has pretty high coefficient of friction, okay? Um, and many other surfaces, right? Okay? So yes, answer to that question. Number 2, why do tires grip the road better on the leveled ground than they do when going up or downhill, right? Well, first, if we were to look at the free body diagram of car going up a hill, right? First, we have FG. And this FG is broken up into, right? Basically, FGY and FGX, right? This FGX contributes to this tire, right? From gripping the road as much as this F normal. As the incline increases, the angle increases, my normal force goes smaller and smaller and smaller. And you know the frictional force depends on your normal force. So if your normal, frictional force, right? Frictional force depends on your normal force. So as your normal force goes smaller and smaller, your grip on your tire gets smaller and smaller, okay? And not only that, this FGX is what's really also contributing from you're going to need more friction to grab the tire, or grab the road, right? So two things that are happening simultaneously that can prevent you from gripping the road better, right? First, because the mg sine theta, which is the force parallel, right? FGX. So that's the obvious one, right? The second thing is, right, the normal force is reduced on an incline, right? Therefore, the force is reduced, the frictional force. Thus, less grip by the tires. I mean, if you take it to the extreme case, imagine this hill like being like this much, like 60-degree hill. You don't even need snow. It's going to be very hard for tires to grip because the normal force reduces significantly, right? Matter of fact, normal force is reduced by half, so your friction goes by half. So as your tires are not going to grip well. All right. Let's take a look at number 3 now. What is the purpose of the curved surfaces called spoilers that are placed on the rear of the race cars, right? Are they designed so the air flows past them, exerting downward force, right? So spoilers are like, it's not only for like, cool looks, actually. Spoilers actually do have mechanical function to this sports cars. If you were to take a look at an airplane wing, okay, so here's an airplane wing. If you take a look at a cross section of an airplane wing, the top part of the airplane wing is actually curved where the bottom is pretty flat out. So when the air flows, right, when the air flows, it flows over in a longer distance, so the air molecule gets spread out a lot more than those are, right, going through the bottom of the airplane wing. So you have a lot less pressure here because density of the air is a lot less than the density of the air here. So you have a lift, right, because of the that's how the airplane wings work, right? Because the air molecule is spread out more going through the top of the wing than the bottom of the wing. So it creates less pressure at the top, so it would actually create a lift this way. However, for spoilers, right? For the spoiler, it is exactly the opposite of the airplane wing. Okay? So even though it looks cool, but it actually has a proper function for this. It's opposite of airplane wings. So air molecules going to the bottom of the spoiler is a lot more spread out, creating less density than the ones at the top, right, which will create more dense than the bottom one. So what happens? It actually, the air density will push this down, like opposite of the airplane wing. And when that happens, when this thing is pushed down, it creates a greater normal force, right? Your F normal increases, so it gives better traction onto your tires. Okay? So, um, And because it creates greater normal force, right, my frictional force is going to be greater, right? Matter of fact, those Formula One cars, they have spoilers up in front, right, and they have spoilers on the back, right. The whole car is designed so that it actually has scooped out bottom like this, so that the whole car behaves like a opposite of airplane wing. Matter of fact, if you go 160 miles per hour on that Formula One cars, they're designed to create so much downforce that you could actually drive up to the side of the wall and then on the ceiling without falling off. That's how much downforce these spoilers can create. But please do not try that with your mom's minivan. Okay, I don't care how many spoilers you put on your mom's minivan, you won't be able to drive on the ceiling of Lincoln Tunnel. Okay, so don't try that at home. Okay, these Formula One cars are made of like carbon fiber and it's lighter than aluminum. And your mom's minivan, it's not that light, I guarantee it. So don't do it. All right, so let's take a look at some problems here. Um, all right, number 4, horizontal force of 12 newtons pushes the block. Right, so this force is pushing up against the wall with 12 newtons of force. Okay, and the weight of the block is 5 newtons of force. So the weight of the block, so Fg is equal to 5 newtons. Right? What's holding it up? Well, the frictional force is holding this thing up. The frictional force is holding it up. If this frictional force is calculated to be greater than 5, it's going to stay up there. But if this frictional force is less than 5, then it's going to slide down. If this frictional force is calculated to be greater than 5, it will still only be 5 newtons because it does not require more than 5 newtons to keep it up. It's because friction is a reactive force. All right. So we can do this so many ways. Sometimes it could get confusing. Now, because this force is pushing into the wall, the action and reaction pair force will create a force pushing out from the wall towards the block, which we call that F normal. Okay, so the normal force is created by how much force was pushed against the wall. So obviously these two have to equal to each other. All right. So let's find out what's going on. Right? Let's find out, first of all, we know F normal is 12, but let's work it out anyway, right? So for the x direction, right, sum of all forces in the x is equal to max, but you know that ax is 0, and sum of all forces in the x direction is equal to, well, you have F, the force push, right, plus the force normal. Right? I'm going to consider this direction to be positive, okay? And I'm going to consider, I don't know, down to be positive. Is that okay? So here, MAX is equal to, right, force push minus, I don't need that sign, minus F normal, because I don't need that sign because I'm going to give directions, okay? But acceleration in the x direction is 0, so force push minus F normal. So my F normal is equal to force push, which is equal to 12 newtons, all right? So my F normal is equal to 12 newtons. That was obvious. Well, now let's take a look at in the y direction. If we take a look at y direction, sum of all forces in y is equal to MAY, right? Sum of all forces in the y direction, I have 2, right? I have Fg plus F friction, so MAY is equal to, I'm going to say Fg is positive minus friction. You know AY is 0, right? So my F friction is equal to Fg. However, what is my friction? That's minimum mu that's required. So mu times F normal is equal to Fg. So mu is equal to Fg over F normal. In our case, my Fg is only 5 newtons, and my normal force happens to be 12, right? So my mu sub s, in our case, comes out to 0.4167. This is the minimum coefficient of static friction required, right? This is minimum mu sub s needed to stay up, right? But we have 0.6, right? So since we have mu sub s equal to 0.6, it will not move. Is that okay? All right. All right. Now let's take a look at part B. For part B, so this is part A. For part B, in unit vector notation, what is the force exerted on the block by the wall? So if we have the block right here, the forces acting on the block by the wall are two forces. One is the F normal. So from the wall to the block, we have F normal. And the frictional force from the wall to the block, like so. Okay. So your frictional force, even though it can be calculated to be like 7.2, right? Because it's 0.6 times 12 would be like 7.2 newtons. But the actual value at this particular instance is only 5 newtons, right? So So even though it can go up to 7.2 newtons, at this moment, because my FG is only 5 newtons, it only requires 5 newtons to keep it staying there. Okay? But this 12 newtons is, the F normal is still going to be 12 newtons. So assuming that this direction here is negative, and then this direction here is positive, right? We're going to say the net force acting on the wall, the force wall, right? The net force wall is that. So the net force wall is equal to the addition of these two, right? Because this is the resultant. Therefore, it is negative 12x hat, right, plus 5y hat newtons. Okay? So even though your frictional force can be calculated to have maximum friction of 7.2 newtons, it only requires 5 newtons to keep it up there because the weight is only 5 newtons. So my actual value for friction will be only 5 newtons. That's the important thing for that problem. Okay? All right. So let's take a look at number 5. Okay. Number 5, a 110 gram hockey puck. So I think it might be a good idea to convert that mass of 110 grams into, right, kilograms. 0.110 kilograms. Okay, convert that into kilograms. And then slides on the ice for 15 meters and it stops. If the initial speed was 6 meters per second, what was the magnitude of the frictional force on the puck during the slide? So what's slowing this thing down? Well, the friction is, right? The friction is actually going to slow this thing down going in the opposite direction of motion. Okay? This is the initial velocity, which is 6 meters per second, and this will be the positive direction then. Okay? Then, of course, we have Fg, right? We have Fg, and we also have F normal going in the opposite direction. Okay? So, well, can we figure out what the rate of deceleration is, right? Because we're going to have negative acceleration, obviously, to slow this thing down. Okay? So if we could say, simply, in the horizontal direction, sum of all forces in x is equal to max. And sum of all force in the x direction is equal to just frictional force. So if we could say max is equal to, right, negative F friction. So this is good to know. If we know our acceleration, we could calculate our friction. But we don't know our acceleration yet. So let's calculate the acceleration of this, which is actually deceleration, because it's going to slow down to 0. So let's write down everything we know for this puck in kinematics. So our initial velocity in the x came out to 6 meters per second. Our final velocity is 0 meters per second. I know delta x, which is 15 meters, is how far it traveled. I want to calculate what my acceleration in the x direction is. This looks like equation number 3 because we don't have time. So my VF squared is equal to VI squared plus 2AX delta X. So 0 squared is equal to 6 squared plus 2 times AX times 15. So negative 36 is equal to 30AX, so my AX is equal to negative 1.2 meters per second squared x hat. So now that we know the acceleration, if we dump it in here, then what do we get? Here, my mass, which is, well, let's bring this here. So the mass times AX is equal to negative friction. So the mass is 0.110 kilograms times negative 1.2 is equal to negative friction. So notice how the negatives will cancel out nicely. So my frictional value comes out to, it should come out positive because I gave direction here already, right? It should come out to 0.132 newtons. Okay? Then for part B, they ask, what was the coefficient of friction between the puck and the ice? Well, now that we know this, so here for part B, now we know frictional force is equal to mu times F normal. So frictional force came out to 0.132. Mu sub K times F normal is just mg, right? So 0.110 times 9.8. So my mu sub K is equal to 0.122 as my coefficient of kinetic friction. All right. Umar, you have a question?
How would like the question change to find out the coefficient of static friction?
Well, since this thing was already moving, you cannot have static friction, obviously. If you have a
Yeah.
static friction, you won't be moving. So since it is sliding already, and then it's coming to a stop, you have to use kinetic coefficient of friction. Does that help?
Yeah. So if VI was 0, would then it be
Correct.
no.
Then
Yeah.
then you have to use kinetic friction static friction to start. But once it starts to move, then you have to use kinetic coefficient of friction. Yeah. Then it becomes a completely different problem if you have two different static coefficient of friction value and kinetic coefficient of friction value. Yeah, then you have to have two different problems. Good. All right. Any other questions before we move on? Alrighty. Let's go on to 6. All right. So here, um, a railroad cart is loaded with crates moving, having a coefficient of static friction. So this here is, right, mu sub s, which is 0.25, right, with the floor. If the train is moving initially at 48 kilometers per hour, so this is the initial velocity right here, initial speed. So VI is equal to 48 kilometers per hour. We should definitely change this into meters per second, okay? So 1,000 meters over 1 kilometer and 1 hour over 3,600 seconds. So if you work it out, you should get 13.33 meters per second as your initial velocity, okay? And then How short of a distance can a train be stopped at a constant deceleration without causing crates to slide? Because what's keeping this from sliding is the coefficient of friction of this times the normal force. The frictional force is keeping it from sliding forward towards the front of the train relative to the train floor, right? So frictional force is keeping it from sliding this way. So here's my friction, right? The initial velocity is in that direction, so I'm going to keep that direction as positive direction, right? And here's my normal force, right? And here's my Fg, right? We don't even know the mass of the crate, and we don't need to. Most likely, you'll see the masses cancel out because we don't have different, frictional values for bigger crates and smaller crates and so on. So let's calculate, right, how much of acceleration this thing can possess before it starts to slide. So what is the maximum acceleration it can possess without sliding? Okay, so sum of all forces in the x direction is equal to max. And then again, sum of all forces in the x direction is equal to just a frictional force. Right? So here, max is equal to, my frictional force is in the negative direction, so negative F friction, which is equal to simply negative mu times F normal is mg, right? So look what happens to my mass. My mass cancels out. So my AX, right, this is equal to mu times F normal, right? So my AX is equal to, right, negative mu, 25.25 times 9.8. Therefore, my acceleration in the x direction is equal to negative 2.45 meters per second squared xn. So that's the maximum deceleration rate it has to possess before it starts to slide. Okay? So knowing that now, let's take a look at the kinematic side of it. So we know the initial velocity is 13.33 meters per second. We also know our final velocity has to be 0. And our acceleration in the x direction is negative 2.45 meters per second squared. And I'm looking for delta x. Looks like equation number 3 because we have no time, right? So Vf squared is equal to Vi squared plus 2a delta x. 0 squared is equal to 13.33 squared plus 2 times negative 2.45 times delta x. So my delta x should come out to 36.3 meters. All right. All right. Next. 68 kilogram crate is dragged across the floor by pulling on a rope inclined at 15 degrees. So here I have 15 degree of tension. Here's my tension. And this tension will have its horizontal and vertical components. Right? So here's my Tx. And here's my Ty. And this angle here is 15 degrees. My Tx is just T cosine 15. Ty is T sine 15 degrees. All right. Well, my other forces, I'm going to have F normal. And I'm going to have Fg. And I will have F friction hindering the motion, right? So if I were to take a look at my x direction, right? Sum of all forces in the x is equal to MAX. Sum of all forces in the x direction, I have two forces, which is simply Tx plus friction. So MAX is equal to, right? MAX is equal to Tx, which is T, well, let's write down Tx first. Tx minus friction. Okay? So since it is static friction, it's not moving, right? So I'm going to try to get this thing budged. So my acceleration at this initial point is 0. And my Tx is T cosine of 15 degrees minus mu times the F normal. We don't know what this F normal is. All right? So let's calculate what this F normal is. So I'm going to leave this here. If I could calculate my F normal, I know my mu, so I could actually calculate my tension. So let's take a look at y direction. So sum of all forces in y is equal to MAY. And then sum of all forces in y is equal to, I have F normal plus Ty minus, plus Fg. And I'm going to consider up direction positive. Right? So MAY is equal to F normal positive, Ty positive, Fg negative. And since my acceleration in y is 0, right, T F normal plus Ty is T sine 15 minus Mg, right? So if I solve for F normal here, my F normal is equal to Mg minus T sine of 15 degrees. So you can actually calculate what your normal force is in terms of T, I guess, right? So my F normal is equal to, okay, Mg, which is 68 times 9.8 minus 0.2588 T. So if you substitute this into my normal force there, you could calculate your tension. So we can say 0 is equal to, right, T cosine of 15 minus mu, which is 0.5, times, right? 68 times 9.8. You should be able to do that, right? 68 times 9.8. 666.4, right? Minus, right? Minus 2.588t, right? So hopefully you should be able to calculate the rest from here, right? So tension should come out to 303 newtons. We will do the part B Friday. All right. Any questions? All right then. Have a nice day. All right. I'll see you Friday. Okay. Take care.
Thank you.
All right.